Hey everyone, how goes it? Welcome back to Computer Science 552 Game Development. I'm your instructor, Dr. J.J. Shepard, and today we're going to continue our discussion around game design and game development. In the past lectures, we have focused on the concepts and the roles related to game production. We began discussing the game design pre-production phase. Today, we continue this discussion by demonstrating a few examples. We turn our attention back to the programmer and continue discussing elements related to the technical design document. We explore even more about game programming today. In a previous lecture, we discussed some values and concepts related to software engineering. Creating a video game is an exercise in software engineering. Software development processes help us to plan and manage the tasks required to creating software. A software pattern is a general, reusable solution to commonly occurring problems within a given context in software design. Some common software pattern categories are structure patterns, behavior patterns, creator patterns, concurrency patterns. We focused on a particular behavior pattern used frequently in game software called the game loop pattern. The game loop pattern helps us organize the game's behaviors into common occurrences. Each game loop iteration progresses the game. The event step involves gathering information about occurrences that have happened since the last game loop iteration and applying the necessary actions related to the event. User input, collision detection, message handling are all common events. The update step modifies the data periodically based on the previous events and data. Moving the player, destroying an asteroid, collecting a coin are all tasks performed during the update. Finally, the draw step displays the results of the update. As mentioned, there are steps that may appear to be outside of the game loop pattern that we need to consider. The initialization event is when all the data or resources for the game are created and set to default values. This event only occurs one time, and it's used to set off the game loop. Within the game code, usually this corresponds to programming functions such as start, begin, and init. In contrast, the finalization event is when all the data is deallocated from our memory. This occurs one time to end the game loop. In the code, this usually is represented by programming functions called end, stop, or destroy. As both of these events only occur once, they could be considered to be outside of the loop, but in many cases it is just a special kind of event. The concept can be used to create most games. However, if we're going to create more advanced games, then we need to consider some additional design and planning. More game features require more sophisticated software structure organization to better organize the behaviors shown in the game loop pattern. Speaking broadly, video game or just game software is the entire collection of the game-specific code, libraries, system, and engines that compose a video game. The game software system is the code which runs or drives the game. Typically, it is the foundational software that calls or invokes the game loop pattern functions that we write in the game-specific code. It contains the software libraries used to write the game-specific code. However, this is commonly considered separate from the game-specific code. As mentioned, this is foundational codes that we build our specific game from. A game engine provides many of the features common in most modern games. We do not need a game engine to make a game, but as a developer, it can speed up the process. We keep in mind that game-specific code is software specifically developed to create a game. It is separate from the game software system. Most commonly, it uses features and programming interfaces that is provided by the game software system. A game engine is a software framework that is used for developing games and includes the necessary software libraries and supporting programs. The game engine contains graphical libraries, physics engines, input managers, audio managers, message passing, and etc. A game engine is not required for making games, but it can speed up the development time. Game software structure can be viewed in a slightly different way than most typical object-oriented design software. Entity Component Systems (ECS) put more stress on composition over inheritance. It focuses on not what it is, but what it does. We keep in mind that composition was another version of association, or the has-a relationship. This is related heavily to concepts in the observer pattern or mediator pattern. The component allows a single thing or behavior to span multiple domains without requiring specific relationships to each other. It is considered a decoupling pattern, and it has a lot in common with a composite pattern, where programming objects are composed of other programming objects. Component-based development emphasizes the separation of specific functionality with respect to a wide-ranging functionality available throughout a given software system. Components for a game are classes of behaviors. We create classes of behaviors instead of classes of things. This is opposed to hard-coding functions or methods within one large monolithic class, meaning we're writing everything in one programming file, or we're writing all the code in one main method. The code for the components are based on the game loop pattern. Separate functions for the events, update, and draw are expected. Typically within a game engine, there are component programming interfaces for which all the components implement the game loop functions. Game objects are the abstract nouns in a game. Every thing in a game is a game object. Every object, player, enemy, rock is a game object. Game objects are considered to be entities in relation to the entity component design. They are simple containers for the components. In many cases, game objects can be considered to be components themselves. Generally, classes are not specifically created for different game objects. There is no class written for player, for enemy, for exploding barrel, for heads-up display. Game engines commonly have universal game object data types, which are not intended to be extended via programming interfaces, but instead just act as a simple container for the components and some additional metadata. Game objects are differentiated based on what behaviors that they perform. The difference is not in the data type, but rather, how does it behave? By using this structure, it allows for the functionality to be abstracted. Many game objects perform the same actions, so they may share the same components. We can see that both player and enemy move and draw. We can consider writing one class move and another class draw, and simply add those to the player and enemy game object. The component's attributes may be different in each instance, but the component effectively does the same thing. A player's speed and an enemy's speed may be different, but they're still moving in the same way. From a functional standpoint, they do the same action, but with different values. Game objects may swap in and out different behaviors. The flexibility of it being decoupled can allow some game objects to either gain or lose abilities. Writing game code requires understanding what are the nouns, the things, and what are the verbs, the actions and behaviors in the game. One way we could start doing this is by noticing the nouns and the verbs when we are reading the game design document. By categorizing the nouns and the verb, this assists in creating the technical design document. Game code is generally composed of game objects, the nouns and things, and components, the verbs and actions and behaviors. This becomes the foundational structure of games. We always keep in mind that communication is fundamental to all parts of this, and as programmers, we are learning how to speak to the machines using programming languages. By identifying the nouns and the verbs, we may speak more clearly to the machines in a similar way that we speak to humans. The game objects and their components are smaller parts of an overall game system. In game design, we discuss how all games are systems. Commonly, the game system is the code which runs or drives the game. It's in charge of calling the functions related to the game loop pattern. These function calls can be considered to be event messages that are sent to each game object and then delegated to the components within. In addition to the game loop pattern, the game's software system is also composed of libraries, other systems, and programming interfaces. It provides the game developer with the features commonly found in games, such as user input interfaces, physics system, and other useful software libraries. The game software system can, for the most part, be considered the game engine. The big overall structure is the game system is composed of collections of components called game objects. Game objects are composed of the behaviors called components. The game system follows the game loop pattern. It handles the events for each game object for each component within. It updates each game object for each component within, and it draws each game object and for each component within. Now that we have that out of the way, we can move to another structure and behavior example. Our problem is to create a space shooter where the player defends themselves from interlopers while traveling through an asteroid field. Once again, we're going to assume that the full game concept has been written in a wiki. You can find this and more details along with it inside the course notes. From the wiki, let's gather some requirements. The player must be able to control a spaceship by rotating it and moving both forward and backwards. The player must be able to fire a laser in the direction that they are facing. Periodically, the game will spawn enemies. Enemies can either be asteroids or space interlopers. Asteroids have a fixed direction and a speed that they will travel. Space interlopers are more intelligent and will track the player and fire lasers at them. Collision detection between the lasers, asteroids, space interlopers, and the players must all be detected. When the player's laser collides with either the asteroid or an interloper, the enemy's health is reduced. When the player collides with either an asteroid, space interloper, or an enemy's laser, then their health is reduced. Destroying a space interloper is worth more points than destroying an asteroid. When the player's health is reduced to 0, the game is over. The game has stages which will increase in difficulty as they progress. The current build will have 5 stages. Each stage will have the same time limit, but the different types of enemies that spawn will increase as they progress. The player must survive as long as possible while earning as many points as possible. When the player either survives through all 5 stages or when they perish, their high scores are then recorded. Once again, let's start identifying the game objects by identifying the nouns in the requirements. We notice a few game objects immediately, like player, laser, interloper, and asteroid. While we do not see it explicitly written, there is another game object that works like a referee, official, or point keeper, and we'll call them the scene manager. Having one game object as the official inside the game can help us organize the overall rules and goals for the game. Many times we can identify the game object when we notice that the game needs information managed, like points, timers, and etc. We also notice that when the scene manager is also related to the stages or the scenes throughout the game. We can now start identifying the actions related to each one of the game objects. Starting with the player, we first notice some of the actions related to user input. Moving the player and firing the laser are actions that must happen based on the inputs by the player. We also notice that it has a transformation component which contains the location, rotation, and scale data. A spaceship is mentioned, and we can think of this as being a 2D image called a sprite. We notice that it mentions collision detection, and we're going to use a simple geometry called a collider to detect collision among other colliders. Collision detection is important, but we need something that handles the collision response. These events are sometimes very specific to the game object, and we need to write them specifically. In our case, we do need to handle collisions between the player and an asteroid, player and an interloper, and player and a laser differently and uniquely. This will be different than the collision responses that are written inside the asteroid or interloper. Later, we will discuss in more detail that there are critical differences between collision detection and collision response. We will also see that we have a health system that will work alongside the player collision and response. Putting it together, we can see the design for the player. From the user input, we can move and spin the player, which is handled by the translate and rotate functions provided by the transformation component. The sprite is drawn at the position and the orientation provided by the transformation component, and the collider also uses the position and rotation as well. The collider's messages are then processed by the player's collision component, and we consider the player collision component to be listening to the collider. When a collision occurs, the collider will broadcast an event message to all the components within. The components listening to the collider will execute code based on the collision. We see the player's collision component and will reduce the health of the player within the health component system. We also notice there are two exterior dependencies that we must address. Firing the laser requires us to create a laser game object. Notifying the scene manager when the player has been destroyed is handled by the scene manager game object. We need both of these to complete the player's system, so let's move on to the other game objects. We first notice that the laser needs position and rotation data, so we know a transformation component handles all of this. We also need to draw the laser using a sprite. Firing the laser requires the laser to move. The laser motion component handles the movement of the laser and also the collision response. We could have them separated into two different components, but we decided that integrating it would simplify the design. There are many different ways to design the systems to work, and some are better than others. As long as it works well enough, then it's not a problem. This is another example of where the collision responses are handled in a different behavior than the collision detection. This again is handled by the collider component. We can now see the laser game object and its assembled components. We notice that it's a prefab as we need to dynamically create mini lasers for our game. We notice that the collider and our sprites both use the position property provided by the transformation component. We also notice how the laser move component is listening to the collider. This code is combining the movement behavior and the collision response into one component for more simplified designs. Connecting together the two game objects, we can see how they work together. From the user input component, the player fires a laser which instantiates or creates a new instance of that laser. One major detail is the connector outside of the game object says instantiates. Instantiating is the concept of creating a new instance of this game object, and we can think of this function as being provided to the game object itself. When we instantiate a new instance of a game object in our world, then it creates it along with all of its components dynamically. Moving on to the next dependency, we can see the scene manager code could all be simply written into one component. We are in the business of engineering solutions and not over-engineering solutions. While much of this functionality could be separated into various interconnecting components, it may at the same time be overcomplicating the design and slowing down the game loop. It is a trade-off between writing a few large components versus writing many smaller components. Writing a few large components can be faster within the game loop, but limits its flexibility when adding or modifying features. Writing many small interconnected components allows for more flexibility in code sharing, but it can become too abstract, overly complicated, and slow. Finding a balance, much like in life, is important here. Always ask, what are the troubles and are they worth my time? The functionality related to the scene manager typically details the constitutive rules like point scoring and timers, but also integrates the goals by implementing the win and loss conditions. In essence, they manage the rules of the game, or at least in part of it. Adding the scene manager to our designs, we could see how our health system will notify the scene manager when the player is destroyed. The scene manager game object is fairly simple, but we do notice that it has dependencies as well. We need to be able to create instances of our enemy game objects, the asteroid and the interloper. So now, let's take a look at the actions related to the asteroid. Once again, we see the transformation contains the position, rotation, and scale data. The collider handles the collision detection, and the sprite of the asteroid is used to draw the game object. We also note that it does have some unique components such as aster movement, which incorporates both the motion actions along with handling collisions. Interesting to note, much of this is similar to the laser game object except for its handling and its health system, which is affected by the collision response. Now, we do the same for the space interloper. This is slightly more advanced than the asteroid, but it still shares many of the same components. It is interesting to note that track a player component is used in a similar way as user input. This is where more sophisticated artificial intelligence could be integrated for the enemies. Now, putting them together, we can see the design for this game. We can see the game objects along with their components and how they interconnect. This nearly feels like an entire design, except there seems to be some features missing that it doesn't quite address. We notice that there are stages that progress the game further in difficulty. We don't seem to have this concept in our component designs, but we have mentioned that the scene manager is used to handle this. Also, when we consider most modern games, we do consider them to have menus and other graphical user interfaces. This is yet to be mentioned, and it requires another level of organization. Game objects can be further organized into scenes. We can think of these as being different sections or environments of the game. Different levels, different rooms, different dungeons, etc., which would contain only these game objects and these components. These help separate and organize different sections, stages, or levels of a game. When a scene is loaded, only the base game objects and their components associated with them are loaded. More can be loaded and unloaded as needed. This can help reduce overall load time. Scenes can be used to further structure an overall game. The scene manager helps enforce the constitutive and operational rules of a game. Many times, it does focus on the overall outcome win-loss conditions of a game. Scenes can be used to further structure the game. Different scenes may have different interactions, rules, and objectives. A scene manager can be used to implement the goals and rules that are specific to a scene. It's a special kind of game object that contains all the relevant scene information, such as points earned. It contains the components which implement the rules and objectives such as time limits and win-loss conditions. It also assists in transitioning from one scene to another. Finally, scenes can be organized based on state machines. State machines can be used to outline the flow of the scenes of a game. Boxes are the scenes, which represent menus, levels, and other representations of the game's state. Arrows are the actions required to move from one scene to another. Start and exit are special kinds of states that indicate when the game is being started and where to end. In the technical design document, state machines representing the scenes are very useful for showing the flow and the progress of the game. This is very useful to have in this game design document. This is in addition to having the component diagrams. The scene managers can be responsible for creating these transitions and implementing the scene state machine. This is in addition to the component diagrams which show the inner workings of the game objects and the components. For our game, we can include this in our technical design document. As mentioned, within the technical design document, it is useful to have the state machines representing the scenes. Scenes should be clearly indicated. The name of the scene and its internal scene name. The objectives, the rules and goals of that scene. Other comments related to this should be added for better clarification about the rules and the objectives. List all the outgoing transitions and their related criteria. For example, to this scene when this condition is met. The list of the game objects within the scene. The game object component diagrams for the scene. This includes a rough sketch of the user interfaces and the menus that can be used for finalizing the design. we can start seeing an example of these details for our scenes. Here's the example of the main menu scene, which is also included in the component diagram. We notice each one of the game objects within our system and their associated components. More details regarding each game object and the associated components are within the provided game design document. Now we can see an example of Level 1. We notice that it contains the component diagram mentioned earlier. Skipping ahead a few scenes, we notice Level 5 appears to be the same component diagram. In fact, much of this seems to be the same except for the transitions, the amount of time that the player has to survive, and the density of enemies. We notice that this is the same structure for Scene 2 through Scene 6. All of these are variable properties that can be set in the Scene Manager component for specific levels. Now, by creating one scene, we could replicate it and adjust some of the Scene Manager properties to increase the difficulty. Now, let's design another kind of game. This time, we're going to focus on creating another type of game called a platformer. The goal of these types of games is to go from point A to point B as quickly as possible while earning as many points as possible. Platformers were one of the most popular game genres of the late 80s through the 90s. While not as popular today, it remains a strong game genre for those interested in perilous parkour play. Here are some of the requirements for our game. The player must be able to run and jump around a side-scrolling 2D environment. Forces, such as gravity, must affect the player when either they jump or fall off a platform. The player can only jump as long as they are touching the ground surface. The player's goal is to reach the end of the level and earn as many points as possible. The player collects coins and must defeat enemies to earn points. The player only has a limited amount of time to reach the end of the level. The time left over earns the players points when they reach the goal. There are 5 levels and are rich in platforms, pitfalls, and enemies that progress linearly. When the player collides with one of the enemies, they lose health. Once the player's health is reduced to 0, the game is over. The player can attack the enemies by throwing a hammer, which is also affected by gravity. Enemies also attack by throwing projectiles that are affected by gravity. Now we can start identifying each of the game objects by noticing their nouns. We can see that there is players, coins, enemies, the ground representing platforms, and hazards representing pitfalls. We also see that there is a goal game object which the player is attempting to reach. We notice that the limited amount of time is highlighted as the scene manager. We now understand that the game object which represents the referee or game official is typically used to handle many of the rules and the data that's important to a scene. We also know that this game object will be in charge of transitioning to other scenes later on. We also notice that there's a game object called camera, which is associated with the side-scrolling 2D environment. In order to simulate a character moving in an environment, we have a camera game object follow the player around. Using a camera to follow the player is a very common way to draw the scene. We now focus on the player game object and what it does by noticing the verbs. Once again, we need a sprite to draw. User input allows us to capture the controls related to running and jumping. The transformation component holds all the data related to position, rotation, and scale. The collider detects collisions and the health system keeps track of the player's health. We also notice a special highlighted component called a rigid body. One major detail to note is this type of game requires more sophisticated physics in terms of both detection and response. A rigid body is a common kind of component that applies classical mechanics in a game object. We know that classic mechanics is a branch of physics concerned with the study of bodies in motion which are affected by forces. Remembering Newton's second law, specifically force is equal to mass times acceleration, is critical in this understanding. This component provides means to assign mass to a game object and also apply forces, such as gravity or other external forces on them. It also assumes that the object does not deform and applies the forces strictly based on a rigid body. While this may appear a little complicated, we recognize that it's just another kind of component that falls within the game loop pattern. In terms of design, we are not concerned about the details of how the forces are applied, just as long as they are. Putting together the components inside the player, we can start to notice some of the differences when we use a rigid body. First, we notice that the user input to run and jump are connected to the rigid body. We assume that this will be implemented where running will change the rigid body's velocity, and jumping will apply a force in the upwards direction of the rigid body. Rigid bodies, again, are used to impart classical mechanics and are typically has properties like velocity and methods like add force. We also see that the rigid body listens to the collider. We keep in mind that the collider detects collisions while the rigid body handles the collision response in the form of applying forces. We also handle collision response in our own way by using some constitutive rules related to the health system within the player collision component. Both of these listen to the collider, but one handles applying physical responses while the other handles applying game responses in the form of health. We also notice how there is a bidirectional arrow both from the rigid body and the transformation. In most physical systems, the transformation and the rigid body work together with the collider in order to detect and respond to collisions. The transformation holds the position, rotation, and scale information which is provided to the rigid body and the collider. However, position and rotations are modified by the rigid body's forces that are detected and influenced by the collider. Each component handles a different part, but they all work together to simulate rigid body dynamics. The game object has some external dependencies that we're going to focus on in the projectile, as it has some similar concepts. We can start seeing components regarding projectiles. We recognize that there are some very common components such as sprite, collider, and transform. All of these are again needed to draw, detect collisions, and contain the location data respectively. We also notice that the rigid body as a part of this as well. As the projectile is being pulled by gravity, it needs to be applied forces. In fact, throwing projectiles is applying a force to it. And so the projectile requires this component as well. Adding this new game object to our design, we can see how the player instantiates the new instance of this projectile. We can see how the game object prefab or prefabricated so that the player can create them dynamically as they are thrown. We also notice that there is a message being delegated to add force at the same time. We assume that the projectile is instantiated and the force is immediately applied, thus simulating the act of throwing an object. Before we move to the scene manager, there is another game object related to the player that is important to discuss. Going back to the requirements, we need to focus on the camera game object. In the other games, the player can move freely within the bounds of the environment. The environments were assumed to be small, never moved, and were the exact size as the window frame. However, in this game, the player moves around a much larger space which cannot be reasonably viewed all at once. We must limit the view space for the user and focus on the player's location, zooming into the player's location within a larger environment. In order to do this, we use the concept of a camera object. This will only draw the game objects within a specified window frame, so now that we can create levels that are much larger than our windows. The camera game object, of course, requires a camera component which handles the drawing of the current scene. The component contains all the data related to the size of the window and its frame, and even more details such as the projection type, render layers, and the field of view in degrees. We also notice that the camera game object has a transformation component that will contain its location rotation data. Yet, there's something special that we need to notice about this particular transformation. In our game, the camera must always follow the player. We already know that the player has transformation component, which contains its position data. In fact, the camera's transformation component depends on the player's in order to follow it. This is a common relationship found in many games. This leads us to a few more considerations to be aware of regarding the structure of game code. Most game engines, or most game software systems, assume that every game object has a transformation component. As mentioned, the transformation component holds all the location, orientation, and scale data related to the game object, position in X, Y, and Z, rotation or orientation in pitch, yaw, and roll, scale or the size in X, Y, and Z scales. We think of this as being the same as the move component discussed in previous examples, but more technically, it transforms the local coordinates of a game object into the world coordinates of our game. This is a much larger concept that is discussed at length later. For now, we understand that it contains the position, rotation, and scale data, and it also handles the calculation related to the transformation functions. Translate means to move, rotate means to rotate, and rescale, or just scale, means to change the size. With this in mind, game objects can be further organized into hierarchies. This tree structure generally links together the transformation components of a parent game object to affect the transformation component of a child game object. This is like many other tree structures in computing where it contains no cycles. The topmost game object, the parent in the hierarchy, uses the global or world coordinates as its transformation data. Any child game object's local coordinates or transformation data is only relative to its parent. If the parent game object translates, rotates, or scales, so too will the children game object. Remember, the child will follow the parent. We can also clean up our design slightly by enclosing one game object within another. The enclosing game object is the parent and the enclosed one is the child. We remember that game objects are components and they may have components composed of other components. With all this in mind, we're just aware that enclosing the transformations will modify the enclosed one and we can skip drawing a bunch of extra lines. Adding the camera game object to our design, we can see that there are a parent and child relationship between the camera and the player. Whenever the player moves, thus the position changes, it will change the position of the camera. This simulates the action of the camera following the player around the environment. We also notice that the camera does not have a rigid body component. We consider that only objects that need to be affected by forces directly require rigid body. The camera does not need to be affected by forces like gravity and only needs to follow the player. We can continue to notice this concept when we're creating the ground, hazard, goal, coin objects. We only need to be able to detect the collision, which is why we have the colliders, but we don't need it to be affected by forces. Collision detection is different from collision response. Collision detection is handled by colliders, and the responses are handled by other scripts, which may include rigid bodies. Rigid bodies are only used when we need to impart classical mechanics, like forces, onto the game object. The key tip is rigid bodies are only needed when forces are needed to be applied, such as gravity is a good place to start. Now, putting them together, we can see the rough design for this game. We can start seeing all the game objects along with their components and how they interconnect. The complexity of this type of game is much larger than one of the previous ones we've discussed. In fact, for sake of space, the game objects needed to be combined, such as ground hazard, in the full game design document. These would be separate again for the purpose of the game and not just for the design. We now start to see how we put this all together into our scene. Now we can organize the game into scenes representing the menus, the levels of the game. We notice there are 5 levels and they progress linearly. We also notice that there is a detail not mentioned in the requirements. Some levels have a secret skip that allows the game to be beaten much more quickly. These are great details to put in these diagrams in the case the game may be non-linear and feature levels that branch or even loop. To sum everything up, creating a video game is an exercise in software engineering. Recognizing common software patterns is critical to quickly developing solutions. The game loop pattern is a behavior pattern facilitated by the game system. Events, update, and draw are the steps. Game systems are structured based on game objects which contain components, which are based on the entity component system, and for games, the component pattern. Game objects are simple containers for behaviors that we call components. Components are classes of behaviors that represent the actions that the game objects can perform. We further organize game objects into structures called scenes that are represented by state machines. This information is all found in the game design's technical design document. Now that we've seen a few examples of how to design a game's software in practice, we only need a few more details before we can finally start developing a game fully. With all that being said, make sure to practice speaking nicely to the machines, and I'll speak at you next time. Now it's time for a bonus round. What is a scene? A scene is a container for game objects related to a section, stage, or level of a game. What is a scene manager? A special kind of game object that implements the goals and rules related to a specific scene. What kind of structure is best used to diagram scenes? State machines can be used to outline the flow of the scenes for a game and should be included in the technical design document. What is a transformation component? The component that contains the information related to the object's location, rotation, and scale. How are transformation components related? In a transformation hierarchy, where the tree structure creates a parent-child relationship between two transforms, the child will follow the parent.